All right, my good friends, I want to welcome you back to Unit 16. This is Reaction Kinetics. We're beginning the fourth installment. Now, this is going to be covered in 12.4, the Integrated Rate Law of the Zumdahl book, but I do want to tell you that I'm going to vary the order just a little bit. I think I can explain it just a bit better if I take a different tack, and so allow me to do that. I think it'll help. I think it'll be helpful. Also, I think I'm going to divide this one up into a couple of different videos. We need to slow down just a bit here because this is a lot to absorb, and I think we would be better off if we just slow down just a bit and cover this in multiple videos. So here we go, Unit 16, Reaction Kinetics. So we've looked at the differential rate law, right? The differential rate law. What do we mean by the differential rate law? Well, we've taken a look at situations in which we have multiple trials, maybe 1, 2, and 3, and we're varying the concentrations in this, varying the reaction rates, and we're taking a look at what the impact of varying a concentration is on a reaction rate. So we use that to determine the exponents, and we were able to write a differential rate law that looks something like this. Rate, remember, was equal to some value that we call K, a rate constant, times the concentration of the reactants. I'm going to say the reactants in this case are A and B. To some concentration, I'll call that little m and little n. So it was our responsibility to examine the data, make sure that we understood what was going on, and then to look to see what the impact of changing various concentrations was on the reaction rate. From that, we could derive the exponents, the m and the n. So then we had it all. Then we had the rate, we had the K, we had the concentrations, and we could determine the rate for any combination of concentrations of A and B. It didn't matter what they were, because now we have K, we have M, and we have N. All right? So that was great. That was very useful. But sometimes the data comes at us in a different form. Sometimes what we get is time and concentration data, right? Time and concentration data. I'm completely making these numbers up. Let's say every 10 seconds we take a reading, 0, 10, 20, and 30. I'm just taking data every 10 seconds. And I'm finding that the concentration of A is diminishing. It's coming down gradually, right? Let's make that a 40. It's coming down little by little, right? That makes sense. But we wanted to write a rate law, right? So we're not going to be able to write a differential rate law. We're going to use calculus. Actually, we're not going to use calculus. Calculus is used to form something called, or derive something called, the integrated rate law. You will not be responsible for doing the calculus. All you have to know is the end result of that calculus, all right? And I'll show you how to do that. So we're going to start with zero-order reaction rates. Zero-order reaction rates. Now, when we're talking about the differential rate law, we said if it was zero order, we're going to write the reaction like this. Rate is equal to K to the 0 power, right? The exponent was a 0 because we determined that it was a zero-order reaction. But anything to the 0 power is 1, so we can just cross that out. So we have rate is equal to K times 1, which is equal to, well, K, right? So rate is equal to K for a zero-order reaction. That makes sense. Now, for a zero-order reaction, the rate is constant. It doesn't matter how much reactant you put into the reaction vessel. The reaction rate is constant. It's not determined by the concentration of reactant at all, right? So now let's talk about the star of the show, the integrated rate law for a zero-order reaction. Here it is. Ready? It is the concentration of A equals minus K times T plus A sub naught. Now you're probably thinking right now, wait a minute, that looks very familiar. That looks like the formula for a straight line. Y equal mx plus b, where b is the y-intercept and m is the slope. And you'd be right, right? You'd be absolutely right. So here's the bottom line. If you plot time versus concentration and you get a straight line, you're dealing with zero order kinetics. All right, you're dealing with zero order kinetics if you plot time versus concentration and you get a straight line. So in this case, the plot of concentration of A versus time gives us a straight line. So we've got zero order kinetics, right? The slope, by the way, is negative K. And you'll see why it's negative in just a moment. It says the expression for the half-life of a zero-order reaction can be obtained from the integrated rate law. So once we have the integrated rate law, this is it, again, for a zero-order reaction. If you tell me the initial concentration that you started with, and you give me the K value, right? You give me the K value, I can tell you what the concentration is of the reactant at any given time, right? At any given time. All right, so that's fantastic now. So now we know the differential rate law, we know the integrated rate law. Let's sweep up here. Folks, what do we mean by half-life? Well, let's just say that I have a reactant. I'll call it A, and A decomposes to form B and C. All right? The half-life is the time, let's say in seconds, required for half of A to become B and C. Let me say that again. The half-life is a time. It's a time, usually in seconds. It's the time required to convert reactants to products, right? Reactants to products. And this is the formula for that line. T1 half for a zero order reaction now. This is for zero order only. This one is for zero order. Okay? Here we go. For zero order, it's A sub naught, that's the initial concentration of A, divided by 2 divided by K. All right? So we can immediately see then that T1 half is dependent on initial concentration of A, and of course is also dependent upon K. So let's use this information now that we've got, this knowledge that we have acquired, to look at a couple of different situations and even solve a problem. So this is our line, right? This is a graph of, let me raise that just a bit. I think I went a little bit too far. Here we go. We have the concentration of A versus time for a zero order reaction. It's beautiful, isn't it? It's a straight line, right? It's a straight line with a negative slope, but it's a straight line. Doesn't matter that it's a negative slope. That slope is the negative of K. If you can determine the slope of that line, it's not hard to do. You've got the negative K and just reverse the sign, and then you've got K, right? So remember, it's rise over run. Change in A divided by change in T will give you the slope, right? So slope for a zero order reaction, the slope of the line that you get with the integrated rate law will give you the negative K. Take the negative of that, and now you've got the K. Notice also from this graph that the half-life time is changing, right? Well, that makes sense. We saw that in the half-life reaction. We said that half-life time depends upon initial concentration. So it makes sense that the half-life continues to change as the reaction proceeds, right? All right. So that's that. That's a nice graph. Let's take a look at this problem. Let's do one on our own now. It says, plot the following data and determine K and write the integration rate law and finally determine the half-life of this reaction. That's a lot, all right? But we're going to have to just break this down, all right? Don't let it intimidate you. Just break it down. Here we go. We know the time is changing. It's 10-second intervals, 0, 10, 20, 30. Concentrations are going down, 2.0, 1.5, 1.0, and 0.5. Let's start by, I tell you what, let's start by graphing this baby. All right, so here we go. All right, on the X, and by the way, I just made a quick sketch. You can do a lot better job than I did, all right? So you do a better job than I did because you have a ruler and you have graph paper and all that stuff. I don't have that. So on the X-axis, I've got time. On the Y-axis, I've got concentration of reactant, right? So I simply plotted as best I could, but I plotted 0 and 2.0 for the time and the concentration respectively, 10 and 1.5, 20 and 1.0, and 30 and 0.5. Look what I get. Get a straight line with a negative slope. So when I plot concentration versus time for this data, I get a straight line with a negative slope. What does that tell me? It tells me zero order, all right? That's the order of this reaction. It also tells me concentration does not play a role in the rate of this reaction. It has a constant rate. Doesn't matter how much of the reactant A that I put in, the rate is going to remain constant. All right? Now let's talk a little bit about K. Well, remember that K was the slope, excuse me, I was going to say it was the slope of the line. It's actually not the slope of the line, it's negative the slope of the line. But let me get the slope of the line. It's the change in Y divided by the change in X. That's the change in A divided by the change in time. And so we get, I can pick any points I want. It's the concentration is changing 0.5 moles per liter every time we take a reading, and every 10 seconds we're taking a reading, so it's 0.5 divided by 10, we get 0.05 moles per liter per second, right? Don't forget to take the negative of that, right? So it was negative first, but then we took the negative of that, 0.05 moles per liter per second then is our K. So now we've got our K. We've sketched it. We've got our K. What else can we do? Well, another thing we can do is we can write the integrated rate law, right? We can write the integrated rate law. And remember, the integrated rate law was concentration, that was the Y, is equal to minus the K times time, that's a variable, plus the initial concentration. Where did I get the K? Well, I got it from this calculation right here. Remember, K was equal to 0.05 moles per liter per second. So that's where I got that. But where did I get this? Where did I get the initial concentration of A? Look at the data. Look at the data. Originally, after time equals 0 seconds, I had 2.0 moles per liter. I simply stuck that number right here for the y-intercept, okay? So that's it. Now I've got the integrated rate law. One last thing. Let's write the half-life. We'll determine the half-life, okay? What's the half-life? So here's what I'm going to do. I'm going to take the initial concentration. Let's start with the 2.0, right? Because it's going to change. But when the initial concentration is 2.0, right? When it's 2.0, then I'm going to have T1 half is equal to, remember this formula from before, A naught over 2K. So that's going to be 2.0 that I'm starting with divided by 2 divided by K, which is 0.05. That's equal to, let's see, 2 and 2 are going to cancel away, and I'm left with 1 over 0.05. That's equal to 20 seconds, right? Now keep in mind once again that the half-life changes for zero order reactions. If I take a look at initial concentration, say, of 1.0, it's going to change my half-life. But for now, for this initial, for the very first reading, I have a half-life of 20 seconds. In other words, in 20 seconds, half of my reactant will be gone. Folks, I think this is a good place to stop, catch our breath, look over this material, and then take a look at first order reactions in the next video. I'll see you there. Thanks. Bye-bye.